This video is unlisted right now. The stream hasn't started yet. Okay, the video is public now. Can everyone hear me? Hello? Okay, so I'm going to be studying discrete math again. I'm just going to start the next chapter. Last chapter, I was reading about trees. It was just like a 40-minute stream. This stream will also be small. It's about planar graphs. So, when connected graph can be drawn without any edges crossing. Should I clear the work from my last stream? I'll just empty it. Um, when is it possible to draw a graph so that none of the edges cross? If this is possible, we say that the graph is planar, since you can draw it on the plane. Uh, guess this is planar because if you bring this dot up here, then it becomes planar. Notice that the definition of planar includes the phrase "it is possible to." This means that even if a graph does not look like it is planar, it still might be. Perhaps you can redraw it in a way in which no edges cross. This is planar because this can be redrawn like this. Yeah, what are they doing here? Oh, they bought this dot downwards. They bought this dot below these three dots. So the three dots are here. This dot stays in place. This dot is brought down. The graphs are the same. So if one is planar, the other must be too. However, the original drawing of the graph was not a planar representation of the graph. When a planar graph is drawn without edges crossing, the edges and vertices of the graph divide the plane into regions. We call each region a face, and the graph has three faces. Yes, we do include the outside region as a face. The number of faces does not change no matter how you draw the graph. Wait, when a planar graph is drawn without edges crossing, the edges and vertices of the graph divide the plane into regions. We call each the graph above has three faces. Okay, so this is one face, this is one face, and then the outside region is one face. The number of faces does not change no matter how you draw the graph, as long as you do so without the edges crossing. So it makes sense to ascribe the number of faces as a property of the planar graph. You can only count faces when the graph is drawn in a planar way. For example, consider these two representations of the same graph. If we try to count the faces using faces including the outside but drawing the graph with a planar representation, shows that in fact there are only four faces. 1, 2, 3, and then the outside. Draw a planar graph. with 5 vertices and 5 edges. How many faces does your graph have? Okay, let's see. Uh, 5 vertices and there's a what? 5 edges. One, two, three, 4, 5. This is only 2 faces, right? 2. Now add a single edge to your graph between 2 vertices that are not already adjacent. So I guess these two are not adjacent. Assuming the resulting graph is still planar, is the number of vertices, edges, and faces it now has. Vertices is still 5. Edges is now 6. Faces is now 3. Add another edge to this graph to the graph, this time to a new vertex. Assuming the resulting graph is still planar, list the number of vertices, edges, faces. So vertices is still 5, edges is now 7, and faces I'm assuming 4. 1, 2, 3, and then 4 of the outside. Oh, no, no, no. We need a new vertex, right? Vertex and an edge. So 1, 2, and 3. Now draw at least 3 more connected planar graphs, each with at least 6 vertices. Count the number of vertices, edges, and faces for each graph and record. Okay, I'm not doing that. Do you notice any patterns? What happens to the numbers if you add an edge between 2? Okay, let's do this previous one. Suppose G is a planar graph. It has 23 edges and 8 faces. How many vertices does G have? Is it 23 edges? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 23, 15, 16, 17, 18, 19, 20, 21, 22, and then 23. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it 23 edges? Okay, let's draw a vertex outside. Let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's draw another vertex here. 1, 2, 3, 4, 5, 6, 7, 8. 8 is the outside. And then 1, 2, 3, 4, 5. Oh my gosh. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3. So how many vertices does this have? 1, 2, 3. It's going to take a long time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Does it need to have 17 vertices? Okay, let's try this. 13 edges and 8 faces. So what we will do is we will remove an edge from here. They said 13 edges. 1, 2, 3, 4, 5, 6, 7, 8. Let's try 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, this is too much. Let's try removing this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, well, I get confused with the counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 edges, but I also need 8 faces. 1, 2, 3, and then 4 outside. So her question is, okay, I can remove this. There was an edge here, and then I can add an edge over here. 1, 2, 3, 4, 5. How about I add an edge here, edge here, edge here. 1, 2, 3, 4, 5, 6. Counting this is so difficult. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 13. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there are 8 faces now. 1, 2, 3, 4, 5, 6, 7. And 7 vertices. Do you notice any patterns? What happens to the numbers if you add an edge between two non-adjacent vertices? What happens if you add a new vertex connect it to an existing vertex? Well, if I uh, if I have a vertex and then I add it to an existing vertex, no new face is formed, but one edge is formed. But the thing is, what happens to the numbers? If you add an edge between, okay, but if I add a new edge, if I add a new edge, then a new face is formed. So this, 1, 2, 3. There is one face, two face, still one face. I should keep a tally. Vertex, edges, faces. So 1, 2, 3. 1, 2, 3. 1, 1. I added one more, and then 1, 2, 3. There are 3 faces. If I add another edge, I have another 1, 2, 3, 4, 5. 1, 2, 3, 4. Now I have 4. If I do this, any other vertices, uh, two more edges. One, two, three, four, five. I think this is wrong. Should be like this. Three, four, five. There is a correlation, but if I add a new edge, a new face is formed. Every time add a new edge, unless I'm adding a new vertex and then I'm adding an edge, then a new face is not formed. But if I'm adding an edge between two non-adjacent vertices, already existing non-adjacent vertices, then a new face is formed. Conjecture an expression that involves the number of vertices, the number of edges, and the number of f that remains constant for all connected planar graphs. So what is constant? So vertices, one, two, three, four, five, six vertices, six. One, two, three, four, five, six, seven, eight, nine, 10. One, two, three. Actually, I should just do this. One, one, two, three, four, five, six, seven, 8, 9, 10. 6, 10, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, 10, 6. Okay, let's remove this. Now let's see. Well, I still have 6 vertices, one less edge. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1, 2, 3, 4, 5. Yeah, 5 edges. Between the edges and faces, I can understand. Remove one edge, remove one vertices. One vertex is gone, one edge gone. Faces remain the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's remove just one edge. 5 vertices. Edges is 7. And then faces is 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 7 edges. Let's try to remove the this vertices as well. One less edge. Number of faces remain the same. Uh, Try to remove this. 1, 2, 3, 4. 1, 2, 3, 4, 5. 5. 1, 2, 3. Yeah, there is a pattern. And I'm getting confused. No, let's remove one edge first. Remove one edge and the 4 vertices remain. Thing goes down to 2, right? If I 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. Four vertices, one, two, three, four, four edges, and then two faces. Four vertices, one, two, three, four, five edges, one, two, three faces. Okay, if I'm adding, okay, let's see. But we need more conditions, right? To have an expression. And a connected graph can be drawn without any edges crossing. Are there any more conditions? I can't think of a conjecture. I feel like I should. Or maybe some information is missing. There's a connection between the number of vertices, the number of edges, and the number of faces in any connected planar graph. The relation is called Euler's formula. For any connected planar graph with v vertices, e edges, and f faces, we have v minus e plus f is equal to 2. 4 minus 4 minus 4 plus 2. 4 minus, okay, minus and then plus. 4 minus 4 plus 2 is 2. 4 minus 5 is minus 1 plus 3 is 2. 4 minus 6 plus 4, we get 2. 5, 6, 7, 8, what? 5, 5, minus 7 is negative 2. 6, 7, 8, negative 3 plus 5, 2. Yeah, that is true. But I cannot imagine why that would be the case. Minus 4 plus 6 is 2. What is the proof? Or is it a conjecture? Why is the Euler formula true? One way to convince ourselves of its validity is to draw a planar graph step by step. Start with a graph P2. For any connected graph, besides just a straight single isolated vertex, must contain this subgraph. Now we build up to a graph by adding edges and vertices. Each step will consist of either adding a new vertex connected by a new edge, or to part your graph to create a new spike, or by connecting two vertices already in the graph with a new edge, completing a circuit. Okay, what do these moves do? When adding a spike, okay, we add a spike here, the number of edges increases by 1, the number of vertices increases by 1, the number of faces remains the same. Also, the increase by 1 and increase by 1, they cancel each other out. But this means that V minus E plus F does not change. Completing a circuit adds one edge, adds one face. What do you mean complete a circuit? Complete. Okay. So we have this over here. make a new edge. So completing the circuit adds one edge, adds one face, keeps the number of vertices the same. So again, v minus e plus f does not change. Okay, so each step will consist of either adding a new vertex, okay, connected by a new edge to part your graph, or by connecting two vertices already in the graph with a new edge. Since we can build any graph using a combination of these two moves, and so never changes the quantity v minus e plus f, the quantity will be the same for all graphs. But notice that our starting graph, P2 has v is equal to 2, e is equal to 1, and f is equal to 1. So v minus e plus f is equal to 2. The argument we have outlined above is not quite correct, since we have made the unjustified assumption that all graphs can be built up from P2 using only the two moves we described. To avoid this issue, you can use a minimal criminal argument. You are asked to do this in the exercise, but the idea is essentially the same as we have here, except we start with a minimum connected planar graph that does not satisfy the formula, then remove either an edge or a vertex to get a smaller connected planar graph that does satisfy the formula. For the complete graphs K and we would like to be able to say something about the number of vertices, edges, and if the graph is planar, faces. Let's first consider K3. How many vertices does K3 have? How many edges? So for complete graph K, and we would like to say something about the number of vertices, edges, and faces. Wait, I forgot by hold on, by part rate, by partite graph, a graph for which it is possible to divide the vertices into two disjoint sets, such that there are no edges between any of the two vertices in the same set. Okay, okay. So this can be in one group, this can be in one group, because there are no edges connecting these and there are no edges connecting these. So all the vertices can be in two disjoint sets. Why is this highlighted now? Not all graphs are planar. If there are too many edges and too few vertices, then some of the edges will need to intersect. The smallest graph where this happens is K5. So this line can go above, this line can go this way, but then this line is stuck. It can't go out right because it's covered by this edge. We try to redraw this without any edges crossing, quickly get into trouble. There seems to be one edge too many. In fact, we can prove that no matter how you draw it, K5 will always have edges crossing. K5 is not planar. The other simplest graph, which is not planar, is K33. 1, 2, 3, and then 1, 2, 3. In a bipartite graph, does all of them have to be connected? I can't remember that. So if it's not connected, is it still bipartite? Uh, bipartite. We say a graph is a bipartite if the vertices can be divided into two sets. If each vertex in A is adjacent to all vertices in P, the graph is a complete bipartite set. Oh, so there is a name for that. A complete bipartite set means that one group connects, like have all the connection to the other groups. Note that the similarities and differences in the proofs, both are proofs by contradiction, and both use Euler's formula to derive the supposed number of faces in the graph. Then we find a relationship between the number of faces and the number of edges based on how many edges surround each face. There is This is the only difference. Okay. Why is K5 the smallest? K5 is the smallest. Can there be K4, which is no, there can't, right? A cube is an example of a convex polyhedron. Contains six identical squares for its faces, eight vertices, and 12 edges. The cube is a regular polyhedron, also known as a platonic solid, because each face is an identical regular polygon, and each vertex joins an equal number of faces. There is exactly four other regular polyhedra, tetrahedron, octahedron, dodecahedron, and icosahedron with 4, 8, 12, and 20 faces respectively. How many vertices and edges do each of these have? I think you have to use the same formula. Another area of mathematics where you might have heard the terms vertex, edge, and face is geometry. A polyhedron is a geometric solid made up of flat polygonal faces joined at edges and vertices. We are especially interested in convex polyhedra. Complex convex polyhedra, which means that any line segment connecting to 2 points on the interior of the polyhedron must be entirely contained inside the polyhedron. An alternative definition for a convex uh, for convex is that the internal angle formed by any two faces must be less than 180 degrees. Um, any line segment containing 2 points on the interior of the polyhedron must be entirely contained inside the polyhedron. Notice that since 8 minus 12 plus 6 is 2, the vertices, edges, and faces of a cube satisfy Euler's formula for planar graphs. This is not a coincidence. We can represent the cube as a planar graph by projecting the vertices and edges onto a plane. One such projection looks like this. Okay, so the edges of the cube are here. In fact, every convex polyhedron can be projected onto the plane without edges crossing. I'm still confused by the definition of a convex polyhedron. Okay. Let me see a picture. Convex polyhedron. The line segment joining 2 points on the surface of the polyhedron entirely lies inside or on the polyhedron, then it is said to be convex. If the line segment joining any 2 points on the surface of the polyhedron entirely lies inside. So this is convex, this lies outside. This I think is not convex, right? What's the difference between convex and concave? Convex is like going outwards, concave is going inwards. I get confused between the two. Internal angle found by any two faces must be less than 180 degrees. So what about a tetrahedron? Internal angle found by any two faces must be less than 180 degrees. Line segment connecting any 2 points on the interior must be okay. They said the same thing. So if I have a dot on the top and the bottom and I connect them, this line is entirely inside the cube, right? If I have another shape, something like this, something uh like this polygon here, or like this 3D shape top. I should, I have to say, if I draw a line here, this line would be outside, like this. You can imagine this line going outside the shape. So this is not a convex polyhedra. Every convex polyhedra can be projected onto the plane without edges crossing. Think of placing the polyhedra inside a sphere with the light at the center of the sphere. The edges and vertices of the polyhedron cast a shadow on the interior of the sphere. You can then cut out a hole in the sphere and in the middle of one of the projected faces and stretch the sphere to lie down flat on the plane. The faces that was punctured becomes the outside face of the planar graph. The point is, we can apply what we know about graphs to convex polyhedra. Since every convex polyhedron can be represented as a planar graph, we see that Euler's formula for planar graphs holds for all convex polyhedra as well. You can also apply the same sort of reasoning we use for graphs in other contexts to convex polyhedra. For example, we know there is no convex polyhedra with 11 vertices, all of degree 3, as this would make 33 over 2 edges. To conclude this application of planar graphs, consider the regular polyhedra. We claim that there are only 5. How do we know this is true? We can prove it using graph theory. There are exactly 5 polyhedra. Recall that all the faces of a regular polyhedron are identical regular polygons and that each vertex has the same degree. Consider four cases depending on the type of the regular polygon. Each face is a triangle, and f be the number of faces. There are then 3 f over 2 edges. Wait, what? Each face is a triangle. Let f be the number of faces. How did they get 3f over 2? Using Euler's formula, we have this, so this. Now each vertex has the same degree, say k, so the number of edges is also kb over 2. Putting this together gives this, which says k is equal to 6f over 4 plus f. Both k and f must be positive integers. Note that 6k over 4 plus f is an increasing function for positive f bounded above the horizontal asymptote at 6 over k. 6 is equal to k. Thus, the only possible values for k are 3, 4, and 5, each of which is possible. To get k is equal to 3, we need f is equal to 4, this is a tetrahedron. K is equal to 4, we take f is equal to 8. The octahedron for k is equal to 5, take f is equal to 20. The isosahedron. Thus, there are exactly 3 regular polyhedron with triangles for faces. Recall that all the faces of a regular polyhedron are identical regular polygons and each vertex has the same degree. A regular polygon, each face is an identical regular polygon and each vertex joins an equal number of faces. So this over here, there are 3 regular polyhedra with triangles for faces. Now case 2, each face is a square. Now we have edges is equal to 4f over 2, which is equal to 2f. Edges is equal to 2 times the face. I don't understand how they're getting this. How is edges is equal to 2 times the face? Maybe if someone can explain that, that would be nice. So we get this. Counting edges using degree k for each vertex gives us this. This is an increasing function. In a 6, this asymptote is k. Any larger value of n will give us an even smaller asymptote. If a no regular polyhedra will exist, the base is larger than pentagons. This is case 4, this is case 3. There's only one regular polyhedron with square faces. So each face is a pentagon. A dodecahedron. This is the only regular polyhedron with pentagons as faces. There are no regular polyhedra, therefore no regular polyhedra exist. Faces larger than the pentagons. Yeah, this last section, I don't. Okay, if someone can explain me how they got these formulas, there are then 3f over 2 edges. How did they get this? Uh, yeah, otherwise, I will then end the stream here, and then next stream, I will just start studying the next chapter. Anyways, see you guys next time. Bye.